Hello everyone, I'm Rekha Murthy, Assistant Professor from Department of Electrical and Electronics Engineering. Today I'm here to explain the experiment related with the Electrical Machine Laboratory 1. The experiment which belongs to cycle 2 is the separation of hysteresis and eddy current losses in a single phase transformer. So as the name suggests, the hysteresis and eddy current losses, though those belongs to the iron losses category. So as we have studied in the transformer, there are two losses. One is iron loss or the core loss and copper loss. So under the iron loss, we have the hysteresis and eddy current losses. Usually the core loss is a constant loss. Suppose if you're going to vary the voltage and the frequency, it will affect the iron losses. So hysteresis loss is usually proportional to the frequency and eddy current loss is proportional to the square of the frequency. So here the transformer is operated with a frequency and voltage changed. Usually it will be constant, but here in this experiment, to get a value of this losses separately, right? So the transformer will be operated with the frequency and the voltage changed in the same proportions. The flux density will remains unchanged. So hence, the no load current, it is going to remain unaffected. So for any transformer, the ratio of voltage and frequency is proportional to maximum flux density. For any value of this ratio, core loss per frequency cycle is given by Pi divided by F, which is equal to A plus B times of F. What is this Pi is? It will be the iron loss divided by the ratio, that is the frequency, which is equal to A plus B times of F. What is A? A and B both are the constants and their values will be determined by the open circuit test on a transformer, which is being supplied by the variable voltage and variable frequency supply. So how to get this variable voltage and a variable frequency to this transformer? So to do that, we are going to connect the DC motor driven alternator to the primary side of the transformer. So during this test, the applied voltage and the frequency to the transformer will be varied together by varying the excitation and as well as the speed of the alternator. But the ratio, that is voltage by frequency ratio, will remain constant, so that the maximum flux density should also remain constant. So here we are going to make use of the wattmeter, which is going to be connected, which is going to indicate the value of the iron loss. So we require one wattmeter, okay, to indicate the value of the iron loss. Then a graph should be drawn, that is Pi divided by F and the frequency. It has to be drawn to determine the constants like A and B. So to know knowing the value of this A and B, hysteresis and eddy current loss components for any given frequency can be determined. Okay, so like this, we need to carry out this experiment. So make sure that usually the core loss will be constant loss. How to get this this constant losses with the without changing of frequency? So the question is, at the primary side of this transformer, we are going to apply some variable excitation or a variable voltage as well as a frequency, such that even the maximum flux density should not change. Okay, so how to get this excitation? By making use of this DC motor alternator setup. So to do this experiment, one question, all the equipments may go around to your mind. What is that? As already I told you, to read this iron loss, we require one wattmeters, right? So therefore, definitely we require one wattmeter. Now you need to think about it. Which type of wattmeter do we require? Which type of wattmeter do we require? Since here the transformer primary side we are going to give some excitation, but on the secondary side it will be kept open. So usually the iron loss will be obtained only during the OC test, as you all know that, right? So under the OC test, the iron loss can be determined. So during the OC test, the secondary will be opened. Due to this, since the you will find very during a no load condition, the transformer will carry very low current, right? That is no load current. So even the current value will be very less, and also the power factor will be very less. So that means we require the LPF, okay, the low power factor wattmeter we require. So that indicates we require one wattmeter which is of LPF wattmeter. How much voltage range do you require this? Definitely on the primary side, this is a single phase transformer, so we require the 300 volt option. So in the wattmeter, you have to select the 0 to 300 volts. Okay, and the current usually it will be 2 amperes. Okay, 0 to 2 amperes. Since the current value will be very less, okay, you if we take 5 ampere, it will be the scale will be very large. So better that we can opt a very less current. So less than the 5 ampere, the range is 2 amperes. So we go with the 2 amperes. Okay, so the wattmeter we require LPF wattmeter 0 to 2 amperes and 0 to 300 volts. Fine. One more thing, what you require is the motor generator setup, which should be connected on the primary side of the transformer, right? Fine. Whenever usually you prefer the motor generator setup, okay, we require that the motor has the motor usually we are taking up the DC motor. Okay, so from the DC motor, because the alternator can be driven by the DC excitation of the stator, right? So therefore, what does the alternator will do? It will produce some AC EMF. So how to get that? So it is taking up the DC excitation through the rotor, then we will get a AC supply. Okay, through the alternator. So that is why before we connect it to the alternator, which has to be driven, that will be connected to the primary, and the alternator is driven by the DC motor. So therefore, the DC motor should be connected to the DC supply. How to start this motor? So we require one starter, that is 3-point starter. So in the 3-point starter, we have 3 terminals. One is L, F, A. What is this? L is line, F is field connection, A is the armature. So to this, we require to start the motor, we require the 3-point starter. So therefore, it will be having 3 terminals, L, F, A. L is directly we need to connect it to the supply. That is DC voltage, 220 volts DC voltage. And F should be connected, that is field means usually you connect it to the usually we connect it to the winding, the field winding. Okay, so the setup will be just like it is a DC shunt motor. Okay, DC shunt motor. So instead of directly connecting to the field winding, we have to make use of the rheostat in order to limit the current. So therefore, we require one rheostat which is of 600 ohm. Which is of 600 ohm, so that so that we can limit the current. Instead of directly connecting it to the field winding, and armature terminal A should be connected to the armature of the motor. That is nothing but the motor. So the setup will be almost, it looks like the DC shunt motor type. Okay. So that is a component we require. And as usual, we are conducting a test on the transformer, OC test. So we require one single phase transformer. Then we require wattmeter, as I told you, which type of wattmeter, how to select that, and 1 voltmeter and ammeter, which is there on the bed. So that we have to, we require that. And also one more thing I would like to tell you, that is here, directly here we are going to use one more rheostat, that is at the armature side. Okay, on the armature side we require one more rheostat, so which is of the range of 150 ohm, 5 amperes. Okay, this is what the setup which you can see. This is almost, it is of a DC shunt type of a motor. So from this it is been connected to the alternator, and as usual we are taking from this point to this point when you measure the voltage, right? This is of the star connection, and here the voltage which we will get is around between the one point of a phase and to the neutral, it will be 230 volts. Okay, so that is why we prefer these 2 points. So we are giving an input to this transformer as a 230. So now we are going to make use of, as usual, the ammeter setup, and as how you did transformer test on a OC test, we had connected one wattmeter, voltmeter, and ammeter. Similar way we are going to connect it. So instead of this, in the first experiment we had an auto transformer, now it is a alternator, right? This is what the AC supply will be generated from this. And obviously the ammeter which you are going to use, it will be 0 to 2 amperes, because no load current value will be very less. So we require that much. And also the voltmeter which will be connected across the stator and the voltmeter. This is how you can arrange this. So this is about the stator connection. What about the rotor? So the field, sorry, that is what about the rotor connection? So this is about the stator connection, because in the alternator we'll be having a stator and rotor, right? So rotor we have to give a DC excitation, then only you can generate the AC EMF, right? So here also you can see a rotor should get DC excitation, so therefore we will connect to the DC supply input. But in the rotor we are going to have one field winding, okay, that is excited by the DC supply only. So we have to connect in series with one ammeter from the DC supply directly to the ammeter. The ammeter which you are going to prefer is the DC only, okay, because rotor is remember that it is excited with a DC excitation, so that is why we require the ammeter which is of a DC type. Then it is been connected to the field winding, and finally we have to close this loop. So this is what the just a series connection of the field winding of the arrangement of a rotor, okay, of an alternator. So this is how very easy to analyze the circuit to draw this. Okay, now before we can just go through the nameplate reading before we conduct the experiment, because we should know that how much the rated current it is and how much will be the permissible value within which we have to apply it. See, usually both of the machine, you can see that the rated speed is 1500 rpm, and it is the DC shunt motor. The rated output is 7.5 HP, and the rated current is 28 amperes. And this is about the DC shunt motor arrangement. And alternator is again the rated speed is 1500 rpm, and the rated output, usually the output of the this machine, okay, that is alternator, usually it will be specified in terms of kVA. So it is 5 kVA, and the rated current is around 16 amperes. Okay, now from this the common thing which you have to remember is the speed is around 1500 rpm, definitely, because both of them has been coupled to each other. So 1500 rpm you have to keep in mind, so that we can start up with the experiment. So this is for the setup where we are going to conduct the experiment, where you can see all the arrangement. This is a rheostat which we are saying it is of 600 ohm, and this is another rheostat which are going to connect it at the armature in series. And here this rheostat is preferable to be connected to this series of this field winding. Okay, so to the field also we are connecting this rheostat, and to the armature side also we are going to connect this armature, so that we can control the voltage and the frequency ratio. Okay, then also we can see that this is a stator arrangement where we it will be having all UVW terminals, and the field winding, this is preferable for the rotor connection, and these are the two connections is preferable here: positive negative supply, the DC supply. And also on the board there will be a DC voltmeter, and the ammeter will be preferable, and also ammeter volt, these are all the AC ammeter voltmeters which will be preferable on that. And this we call it as a dimmer stat, which is going to control the what is that the what is that this is a dimmer stat, okay, which is going to control the frequency, okay, with the variation of the rated voltage. And here the LFA, you can see that this is a respective 3-point starter. So 3-point starter will be having these 3 terminals. So this is a DC starter, okay, through this only the motor will be driven. So L is line, A is armature, and F is the field. Through the respective the connections we have to do. And also there is an applicable of this LPF wattmeter which you are going to use. Since it is an OC test, definitely we require the low power factor wattmeters. Now let us see that how you are going to do the connections. So this is what L is connected to, that is positive supply is connected to the L point, and the field LFA. So first I will finish it off LFA. Then F is connected to the rheostat of 600 ohm. The other end of the rheostat is connected to the field winding Z. The other ZZ terminal is connected back to the negative supply. This I have closed a one loop with respect to the line, and completing through the field connection, and coming back to the negative supply. Next, coming to the armature side. The armature one end is connected to the rheostat, the other end of the rheostat is connected to the motor, the other end of the motor is connected back to the negative supply or ZZ. This is what one complete loop I have closed with related with the motor. Now coming to the alternator side. The U connection is connected to the ammeter. The other end of the ammeter should be connected to the wattmeter M, and MC should be shorted. The L is connected to the transformer, and the other end of this transformer is connected back to the neutral, because I want a 230 volt. So I have taken that tapping. And coming to the next point, that is related with the rotor connection. Okay, on the rotor connection, what we are going to do is the positive supply. The rotor connection, the positive supply is connected to the DC ammeter. The other end of the ammeter is connected to the field. The other end of the field should be connected back to the negative supply. Now let us insert the voltmeter. The voltmeter at the point of a U, and the another voltmeter should be connected at the neutral point. This is how we complete the connection part. Now let us move on with the procedure. So connections will be made as what we have shown here, the circuit diagram. Initially, what we have to do, the motor field rheostat, this should be in the cutout position. Both of the rheostat should be in the cutout position. The DC motor, just to switch on the supply here, DC motor is started by using a 3-point starter and brought to the rated speed. So this we have to vary, so that the rated speed will be observed here around 1500 rpm. Okay, by cutting in the field rheostat if we require it. Then what we have to do, we have to close the SPST switch. This is the SPST switch. Close the SPST switch. Then vary the field rheostat gradually. Okay, so vary the vary the alternator field, this one. Okay, so vary this alternator field rheostat gradually till the rated voltage is applied. Okay, close the SPST switch, vary this dimmer stat, or you can call it as vary the alternator field rheostat, okay, gradually to the rated voltage. So rated voltage will be observed, rated voltage will be observed, okay, and the till the rated voltage, primary voltage is applied to the transformer, okay. Then that is appearing, that is appearing actually okay, that is appearing at this point. Then the frequency, once you get the 230 volt, then by varying this rheostat, the frequency will be varied, okay, by varying this frequency will be varied by varying the motor field rheostat, and the readings of the frequency are calculated, okay, by noting it down the speed. So this above procedure will be repeated for a different frequencies, and the readings will be tabulated. So bring back the demostat to the minimum position and rheostat to its initial positions, and switch off the supply. Okay, this is how we need to proceed with the um, uh, experiment. Then we have to take down the tabulations. That is the we have to note down the speed, then frequent we need to note down the speed, then frequency we have to calculate, then voltage we have to note down simultaneously, speed, voltage, and the iron loss that is indicated by the wattmeter, okay. Then frequency we have to calculate it, and also by using that simple formula, ns is equal to 120 f by p, right? So p is pole, number of pole is 4, so we have to substitute in that way, and we have to find out the frequency. Then wi by f, so this is the ratio we have to find out. Then okay, the second first formula I've already told you. The second formula is the hysteresis law, hysteresis laws, that is wh is equal to a times of f. So the a and b constant should be obtained from the graph. Similarly, eddy current loss also can be obtained, that is W is equal to B times of F square. Even the B should be, it is a constant, that is a slope of the tangent which is drawn to the curve. So when you sum up these two factors, then only we can get the value of a new value of a Wi by F. So this is what the graph we get it. Okay. So this will be the A constant and the B constants. Okay. So this is how we can conduct the experiment to separate the eddy current loss and the hysteresis loss of a single phase transformer. Thank you for watching the video.